A singly charged positive ion has a velocity of 5 times 10 to the 5th meter per second, moving to the right. The ion has a charge of 1.6 times 10 to the negative 19th coulombs. The ion enters a region of uniform electromagnetic fields. Okay, electric field is this, pointing downwards. If the ion is to pass through this region undeflected, okay, undeflected, underline that, then what is the magnitude and direction of the magnetic field? Okay, so some key points to kind of cue in on here. Cue in on? C-U-E, not Q. Okay, this right here, so 10 to the 5th, once you start getting to like 10 to the 6th, you really have to start worrying about relativistic effects. So like 3 times 10 to the 8th is about a little bit over speed of light. And so once you start getting 10 to the 6th, it's like, well, relativistic. But when you're 10 to the 5th, you're pretty much okay to be like, nah, not important. Another thing is, it's like, wow, that's kind of an odd number, 1.602. That's the charge of a electron, of a single electron, times 10 to the negative 19th coulombs. So what this is when it says singly charged, it means it's missing one electron. So this right here is redundant, singly charged, and giving you the charge of the ion, because they're saying the same thing. But I kind of like it because it reinforces that they know what they're talking about. I'm going to assume here the electric field is pointing down like this, because when they say it's in a negative J direction, and then they're saying pointing downward, I'm assuming that that's being redundant and not double negative. Okay, and then undeflected means that, so okay, we're going to draw a picture here. Boom, 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 boom. Positive charged ion moving this way, and we have an electric field. So electric field pointing downward. And then we have some mystery B field that's causing net force to equal 0. So I'm going to write up the equation for force on a moving charged particle. So the equation I use is force equals QE plus QV cross B, where this V is velocity, this is electric field, and that B is magnetic field. And I always write this out whenever I have a moving charge, because a lot of times either the electric field will be 0 or the magnetic field will be 0, or velocity will be 0, and you can cancel something out. I still like writing the whole thing up just to kind of keep my head straight. So what this is saying is undeflected, so we're going to assume that the net force is 0. So what that gives us then, turn this equal sign into an arrow, we get QE equals negative QV cross B, okay? And I'm not going to worry too much about the sign because I'm just going to think of it in terms of arrows and vectors. So we're trying to find what is the magnitude and direction of the magnetic field. So we had this equation, we rearranged it, and I dropped the, everything here is going to be perpendicular, so I'm going to drop the cross product right there, and then just write this as E over V equals B. Now this will give us the magnitude, but not necessarily a direction. So we know that let's see here. So we have, if we look at this part, which is the force of the electric field, we have a positive charge, Q times E. We're going to have force electric going down. And so that means we're going to have a force due to the magnetic going up. And the way we do this cross product here, so we look at just this section, Q, which is positive, velocity, which is going to the right, and then B, which is going to be our mystery. So we're going to do our cross product here. I like to use the right-hand rule. Whatever right-hand rule works for you, this is the one I like. So we're going to do V times some sort of mystery B will give our thumb pointing upward. So if we do V out this way and then B into the board, we see that we're going to have a force going up, which is what we want. So V cross B into the board goes up. So if we do, use a different color just to add a little bit of flair into the board, magnetic field. So we can see that V going to the right, B into the board gives us a force going up. Right hand rule, how to do a cross product. V is the first one, B is the second. So this gives us a magnetic field going up, which is the correct direction we're going to have. And now the magnitude, since everything is perpendicular, this cross product will just be 1. You can think of it as sine of theta, where theta is the angle between velocity and magnetic field. Here, it's going to be 90 degrees. Okay, focus. So E is 1,000 equals 1,000. I'm going to drop the negative because that negative really just tells us the direction. And we already know the direction. Divided by V, which is velocity, not voltage. 5 times 10 to the 5th. So we have 5 times 10 to the 5th. And so now, if we rewrite this a few times, we have 1 times 10 to the 3rd times 10 to the negative 5th over 5. We'll do, this will be 10 to the 1st times 10 squared. We have 1/5 is 0.2 times 10 times, and then combining negative 5th and 2 times 10 to the negative 3rd. I know it looks confusing. I'm trying to simplify things a little bit here. And we get 2 times 10 to the negative 3rd. And then the unit will be Teslas. This will give us 2 milliteslas. So I know a lot of work here and pretty messy. So we're trying to do 2 things. We're given the information that we have a charged particle moving to the right. We have the formula here, force equals QE plus QV cross B. We want to find out what this magnetic field is here. So what we do is, we know that since it's undeflected, the net force will be 0, which means the electric force, which we know is going down, Q times E, is going to be opposed exactly by the magnetic force, which means we're going to have a magnetic force going up. And then analyzing this dot product using the right-hand rule, we find out that to make a magnetic force go up, we have to have a magnetic field going into the board. That's what this circle with a little X means. And then analyzing this from just a math point of view, and then some algebra, we found that our magnetic field will be 2 milliteslas. I'm going to erase most of this just to clean up the board. Put this over here, and it'll be 2 milliteslas. Okay, so that's how I approach that part. Next, the ion enters a region with only a uniform magnetic field of B is 0.75 teslas. Okay? In the K direction means pointing out of the page. Good. I'm glad they told us that, because I'm never quite sure. What is the mass of the ion? Okay? If it moves in a semicircle with radius 0.277 meters. Okay. So first draw a picture. We have our ion. So this will be the region of magnetic field. Moves like this. So this will be magnetic field here. And it said out of the page? Out of the page. So it'll be a circle with a dot in the middle. And force on this particle will be QE plus QV cross B. Same formula I always write up. We have no electric field, so this part will be 0. We know what this is. We know what velocity is. And we know what the magnetic field is. And this is going to result in moving in a circle. So it's going to be mass times acceleration. But this acceleration is going to be centripetal acceleration. And the formula for centripetal acceleration is v squared over r. So this will be mv squared over r. We know what v is and we know what r is. And our only mystery variable is mass. So we can take this, rearrange it, use this portion right here, use that portion right there, do some algebra, mass. I don't like this green color. That's okay, I'm not going to switch horses midstream. So we got mass equals QVB. This cross product here, since velocity is in this plane and the magnetic field is out of the board, we say V cross B, yep. coming out of the board, it'll always be perpendicular, which means the sine of theta, the angle between the two, will be sine of 90 degrees, which will be 1, which means I can basically just drop this cross product there. Because a cross product is just a measure of how perpendicular two vectors are. Are. Okay, put a v squared on the bottom, and then we'll put an r up top. V squared r. That cancels. We get QBR over V. Putting in the numbers, we have 1.6 times, 2 times 10 to the negative 19th. I left off the 0.02. Times 0.75. There we go. 0.75 times radius, which we're told is 0.277. 0.277 all over velocity, which is 5 times 10 to the 5th. Okay, so I'm going to put this in the calculator, but I'm going to leave off the negative 19th and the 5th. Whoop. On clear. So we'll do 1.6 times 0.75 times 0.277 divided by 5. That gives us 0.066 times 10 to the negative 19th times 10 to the negative 5th. When you move the 10 to the 5th on the bottom to the top, it just becomes negative. And I'm going to multiply by 10 squared times 10 to the negative 2. That's the same as multiplying by 1. It just makes it convenient. You'll see in a sec. So then we have 6.6. Make that more of a dot. 6.6 times 10 to the, let's see, this is negative 24, negative 26. 26 kilograms. 24, 26. Yes, I believe so. Make sure I didn't forget any. Yep. That seems reasonable enough. So the mass of this would be really small. Probably like hydrogen, helium atom small. So yeah, I think that's the math of how that works. So long story short, we had a magnetic field, and we were trying to measure the mass spectrometer style. Write up the formula, write up the mass equals acceleration. In this case, acceleration is centripetal acceleration, so v squared over r. Rearrange things, get the mass, do the algebra, find the answer. Not too bad. Good job, go team. How much time did the ion take to move around the semicircle? Okay, so I'm going to assume the semicircle is really just a half circle. Makes sense. What's happening from the magnetic force is it's always pointing towards the center. And that's causing the centripetal force. And so what it's doing is since a velocity is both a magnitude and direction, when you're changing just the direction, the magnitude stays the same. So what we're going to do is we're going to do, let's see, velocity equals distance divided by time. I know that because my car goes in miles per hour. Rearranging this, time equals distance divided by velocity. Distance is 2 pi r. So it'll be 2 pi r over 2, because it's a half circle, divided by the velocity, which they gave us in the beginning. It goes like 5 times 10 to the 5th. Yep, 5 times 10 to the 5th meters per second. Make sure that circle is in meters. It is. And this will be 5 times 10 to the 5th. Cancel. This equals, so we have pi times 0.277 all over 5 times 10 to the negative 5th. Get the calculator. 3.1415. That's about what pi is. I know I could use the pi key. I prefer this. 0.277 divided by 5. And so we have, wait a sec, do that again. 0.174. Not too bad. 0.174 times 10 to the negative 5th. I'm going to do times 10 to the 1st times 10 to the negative 1. And then we get 1.74 times 10 to the negative 6th seconds, which is 1.74 milliseconds. Microseconds. There we go. Microseconds. Almost messed that up. Okay. Well, I still might have messed it up. I might have messed it up with an easy thing to get wrong. Okay, human performance traps. So, long story short, this one, the idea is the magnitude of the speed of the magnitude of the velocity of the ion is constant because the magnetic field, even though it's creating a force and acceleration, the acceleration is acting perpendicular to the direction of motion. Therefore, you have a centripetal acceleration going on there. And you can then just find the distance that the ion travels and then assume a constant speed. So that's how I would approach that one. Bum, bum, bum. Whew, so much writing, so much stuff. Okay. Next, let's see. I'll clean up this part real quick. There we go. Get rid of that. Move this guy over so it doesn't feel so cramped. Don't want to ruin the feng shui of the next problem. Okay. Next problem, part 2. Part 2B. Bravo, potentially. Not sure. So we have a loop of wire which is bent in a semicircle with a radius of 0.4 meters. So 0.4, okay? And carries a current of 10 amps. Okay, 10 amps. The loop is in a region of uniform magnetic field B, negative 0.1 Teslas. Okay, good number, pointing downward. Okay, so 0.1 Teslas. At the instant when the plane of the loop is in the XY plane as shown. What is the force on the straight section of the wire 2R? Okay. So there's two ways to do this. The way I like to do it is I use the same formula I always use. Force equals Q times E plus QV cross B. And then I'm like, all right, so there's no electric field. And we have, so this magnetic field. And you're like, but I don't have any current here. What's going on? Well, first, let's see here. We have current, which is assumed to be positive charges moving in the positive direction. In reality, they're negative charges moving in the negative direction, but that's kind of double negative, and you can just pretend whichever one you want. Positive charges, positive direction is easier to use. So we have charges moving this way, magnetic field going down. So when you look at that, you have V cross B, so you're going to have a force going inward. And specifically, they're perpendicular, so this cross product is going to be 1. So I'm going to make kind of sort of QVB. And if you look at this V, I'm going to rewrite this V as distance L over time. So this is kind of sort of Q times L over T times B. Well, you can move this T over here, and Q, charge per unit time, is the definition of current. So we have I, L, B. And this is more mnemonic than strict derivation. But it is also true. So we have amps, which are 10, times length, which is 0.8, really 0.4 times 2, but I'm happy with the 0.8, and times magnetic field, which is 0.1. And let's see here, what is the force? Yep, they don't ask us for direction. Maybe they do. Force is a vector. We'll do both. So we have 10 times 0.1, that will give us 1. 1 times 0.8 is 0.8, so we have 0.8 newtons. Okay, going back to this portion right here, we want to find the direction. So, make a little vector above the B, do right-hand rule, V, direction of current, bend so direction of current, which is the positive charges moving in the positive direction, which is the V, cross B, which is down, we're going to have it into the board. So force will be into the board like so. And so the answer, what is the force on the straight section of the wire? 0.8 newtons into the board. So both of these are part of the answer. What is the force on the semicircular section of the loop? Okay, so this is, as a refresher, we'll write up the same equation that I've written at least 3 times now, probably 4. QV cross B. Oh, that is so bad. There we go. Close enough. Not much better. So again, the electric field portion cancels out, go away, bam, 0. And now we're just left with this second portion here. And another way of kind of looking at this is, what is the length of the wire that is perpendicular between these two? So you have V, which is the current, positive charges moving in the positive direction like this. What portion of this length is perpendicular to the magnetic field? Well, long story short, at this point here, you're going to have, it's going to be completely perpendicular. At this part here, it's going to be completely in line, because this goes up, which is going to be in line with the magnetic field there. And so this will have a bigger effect, and this will have a lesser effect when producing a force. Long story short, though, you can look at this instead like this. If you take this circular loop, and draw it like this, then it kind of will make sense for the total force. It's like, okay, this portion will provide 0, but this portion will provide 100%. This portion will provide 0 again. And what you're left with is, this is the perpendicular portion of the loop, which is the current carrying wire, to the magnetic field. And so that's the only portion that's going to contribute anything. And so it's going to be the exact same as the loop, which will be 0.8 newtons. Now, one detail here is, if you look at the loop, you're going to do FQV cross B. So V is this direction, B is down, and you're going to have the force here at this point. Force will be out of the board towards us. Therefore, it's going to be, I'll draw a little dot like that. It'll be the same magnitude as the straight wire, but it's going to be in the out towards us, out of the board. So opposite direction, same magnitude. Okay, so now they want to know what the magnetic moment of the loop is. So magnetic moment, I'm going to write it as M, is current times area. So the current is 10 amps, and the area is pi r squared over 2, which will be, see if I can do this in my head. I can't probably do pi in my head, but you'll get the idea here. So we'll do 10 times pi, and then it's 0.8 squared. No, radius is 0.4. So I'll do 0.4, and I'll write 0.4 twice. That way I can, maybe easier to cancel. Yep, I'm good with this. So this will be 0.2, that will become 2, and so we have 0.8 pi. 0.8 pi is the magnetic moment for the loop. So magnetic moment is basically how not vulnerable, how much torque can you get when it's in a magnetic field. Okay. Okay. Purple, blue. Light blue, baby blue, cyan, orange. I don't like orange. All right, blue. What is the magnetic torque acting on the loop? Okay, so this is where the magnetic moment comes into handy. Torque equals M cross B, where this M is the magnetic moment. I know, it's kind of like, it looks kind of like the mass, and that can become really confusing. Maybe we can call this mu, but then it kind of looks like friction. I know, we're running out of letters here. So we have torque equals magnetic moment cross B. Real quick, the magnetic moment is perpendicular to the area using the right-hand rule. So if you wrap your fingers around it, following the current, your thumb would point out of the board. So the magnetic moment here is pointing out of the board like so. So we do this magnetic moment pointing out of the board, cross B, which is going down, and the webcam is flipped, so it's going to look crazy. I should be doing this with my left hand. Not that talented. So magnetic moment out of the board, cross B, I get a torque that's to the right. So torque is going to be to the right. So this will be 0.8 pi times magnetic field, which we already know is what, 0.1. 0.1 equals 0.08 pi. And this will be to the right, that direction. And I'll get a calculator real quick on 0.08 times 3.1415, and it's about 0.25. About 0.25, and then the torque will be newtons times meters. And up here, magnetic moment, forgot to mention this, it's going to be amps times square meters, which is kind of funny because this is an A, that's an A, but that A stands for amps, or that A stands for area, this one stands for amps, that I stands for amps, that's meter squared, which is, try not to get confused between the units and the dimensions. I know, it's excessively confusing, and you really need to have a conceptual understanding to keep everything straight. So 0.25 Newton meters is the torque, and again, that was found by torque equals magnetic moment cross B. One other thing, because even though now we know that the torque is to the right, intuitively that means nothing to me. But what it's saying is, if you use the right-hand rule, I think, place your thumb along the direction of the torque, the wire will spin the direction that your fingers are wrapped. And we already found that earlier here, where this force is into the board right here, and then this force up here is out of the board, and so it's going to be terrible. Don't know if I can do it with perspective. It's going to wrap kind of like, so the semicircle will kind of rotate like so based on these forces that we found, which is one of the reasons why I try and find the forces, and then I use that to intuitively understand what the torque is doing. So I hope that helped with this problem. This is a classic problem, and it's good to kind of have an understanding of how to do them. So appreciate it. Hope that helps. See you next time.